Okay, so let's clarify what happens exactly when we try to differentiate in a feedback system, in a feedback loop, and we try to simulate that. So we had some issues trying to do that in Simulink, and I think it's going to be useful to kind of go through it a little bit. So let me share my screen. I want to go back to our simulation model. All right, so we want to clarify what's happening here. So here I kind of took the controller and the plant that we were testing with. So again, our plant is the ship, right? So it has the ship dynamics, this thing here, integrator, and the 10-second time constant, and then the steering gear dynamics, and then the power amplifier dynamics. And then we said the best kind of controller we could come up with is a double PID. So it's a PID and then another PID. The idea is that we, I guess, let me redo it again. Right, so there is the ship. Okay, so that's the ship. And then, of course, there's an integrator. So I forgot the integrator. So divided by S. And then the gear, and then the amplifier, amp, and then the whole loop gain is going to be, and I want to show it, it's going to be this thing, right? And I could also show it in pole zero form, so ZPK. So previously we wanted to stabilize this. We wanted to add the root locus. Yeah, I'm just right now kind of reestablishing what we already did, right? And we said we wanted to add to this 2 zeros. So if I do the root locus of this, so this is going to be L. It's going to be something like this. And you can see the behavior. Those two poles go towards infinity this way, and the other two poles go towards infinity the other way, and things become unstable because they're going to the right-hand side. And what we said is we wanted to add zeros. And if I recall correctly, we added a zero at 1, and a 0 at 2. And I added the zeros in normalized form. So I added 1 plus S and 1 plus S plus 2. Normalized form meaning that at S equals 0, the gain is 1. So the DC gain is 1. Right? I want to change this now up a little bit. I don't want to keep the 0 at 1 because there's already, I don't want to keep the 0 at 2 because there's already a pole at 2, which is fine. It's not a problem, but just to kind of what you will get is a pole zero cancellation that doesn't affect anything. But just to kind of simplify things a bit, I'm going to put the 0 at a different place. So if I'm going to put the 0 at 3, let's say. So if I put the 0 at 3, I get something like this. Right? Which is also good. You can see the two, so you can see the two poles here. One pole gets attracted to this 0, the other pole gets attracted to the other 0. The two poles that are closer to the origin, they do this behavior, but things are getting better. The two poles are moving away from the j omega axis. So that's fine. So this tells me I can go and pick some gain. So if I select this gain such that the poles are here, right? Beyond this gain, the poles start to go up. And as we go up, we know that the damping, the overshoot gets worse, right? Damping gets less. We are less damped. You can see the damping coefficient getting less. So this is 1960, right? So using this slightly different design, if I go now to, all I've done here is I've replicated the plant and the controller 3 different times. And I'm reading the output 3 different times. The reason is because I want to compare the different scenarios, right? So the key thing here is we want to implement those 2 zeros, right? And we said the best way to implement those 2 zeros are like a PD controller. So you want to use a PD controller. A PD controller, let me write it here, is KP plus KD times S, right? That's what it amounts to. And in this case, 1 plus S is going to be, KP is going to be just 1, and KD is just going to be 1. 1 plus S over 3, KP is going to be 1, and KD is going to be 1 over 3. Okay. So the question is, how do we apply? There are many ways of implementing this. Let me start with the first way, which is this. So here in this case, I'm implementing the PD controller as proportional part. So this is the proportional part here. And this is the derivative part. However, this is the derivative part with an added filter, right? And this is the derivative part with an added filter, added pole at some place. So we have the differentiator d by dt or s. The idea is that this differentiator is by itself is a pole, is a zero at the origin, right? And a zero at the origin, if you give it like a step function or something like that, it's going to give you an impulse, right? So that's and it's going to amplify noise. It's not going to necessarily be a problem if you plug it in theoretically in a full complete block diagram, because there's going to be other parts of the block diagram that are going to interact with it. But in general, we don't want to have an integrator by itself in our design. We always want to filter. We always want to filter that integrator so that it does not react to noise. There's not sorry, differentiator. Differentiator by itself is going to react to noise. So what people do is they add low pass filter. The best way to add the low pass filter is represented as a pole. So we could add a pole at some place on the real axis, and the further away it is from the origin, the less effect it will have on over the whole system. So the less effect it will have over our dynamics. So let's say we add the pole somewhere at 100, let's say, minus 100. So this is the differentiator. And we said we wanted to add a pole at minus 100 to the differentiator to smoothen it out. So the pole would be something like this. It would be 100 over S plus 100. Okay. So I want to put this in a more suggestive form. So let me divide everything by, no, let me keep the 100. Let me divide everything by S. So it's going to be 100 over 100 over S plus 1. And this is now the suggestive negative feedback form. So remember, negative feedback form, alpha over 1 plus alpha beta, forward path over 1 plus forward path feedback path. So the suggestive form is as follows. A differentiator, right? I can write it this, or I can write it as S. And with a pole that filters the high frequency response of it is going to look something like this. It's going to be some gain forward path 100. And then the feedback path is going to be 1 over S. Right? So this is equivalent to a differentiator with a pole at minus 100. Okay, so that's what we've done in the Simulink. Okay, so now going back to here, so this is essentially what this is. This is essentially what this whole thing is. This is a differentiator with a pole at minus 100. And I hope hope I convince you that that is the case. So this is two differentiators. If I look at this by itself, I get this sort of response by itself. So this goes from 0 to 2, and then settles at 1.66. Okay. Now the question is this response correct? So we want to establish some sort, because as when we in class, when we were working with Simulink, we saw some different responses, right? So we want to know we want to have the benchmark and know what is the correct response. So So I'm going to go to another tool. I'm going to go to Mathematica to try to kind of analytically determine what the exact response is. This is something we could do on paper. We already learned how to do this on paper, but I want to do it. And this is also a good exercise to show you how you can do those manipulations, analytic manipulations in a computer algebra tool. So again, going back to the plant is a transfer function, 0.1 over 10s plus 1. Right, so let me erase this. So the plant is going to be 0.1 over 10s plus 1. And it's going to also have an integrator, 1 over s. And then the steering gear is going to be 0.s over 0.5 s plus 1. And the amplifier is going to be 1 over 0.05 s plus 1, 5 s plus 1. So that's the plant. That's the open loop gain of. And then remember, we added a 0 too. So let me see what 0 we added. We added a 0 at 1 and a 0 at a 0 at -1 and a 0 at -3. So let me add the zeros here. Now, this is the open loop transfer function. The closed loop transfer function is just going to be the open loop over 1 plus the open loop, right? That's the negative feedback form. What's this 1 over s? Well, I want to examine what the response is going to be to a step response, right? So I want to take my closed loop transfer function and I want to apply a step response here. Actually, my step response is 1.6. The final, the steady, it's 1.6 u of t, right? So I want to make this 1.6, right? So this is my closed loop transfer function multiplied by the step function. And this should give me the transfer function of the output of this thing. So I took the open loop, I got from it the closed loop, multiplied it by the input. So this is all done analytically. So when I do this, I get TS. I can examine TS by itself. It's going to be this thing. This is just this whole thing combined together. And then I could use the apart function. The apart function in Mathematica gives me something that's essentially the partial fraction expansion. So if I do this, I get the partial fraction expansion. However, also in Mathematica, what I can do is I can take my TS and I can feed it into a function called inverse Laplace transform. So you can look it up. So you can you tell it that S is the S domain variable, T is the T domain variable, and I can get the inverse Laplace transform here. I do evaluate for mathematical reasons. I want to evaluate that expression. I don't want to go deeply into that right now. You can go deeper into Mathematica if you wish. But this is essentially the inverse Laplace transform multiplied by the Heaviside function, because in Mathematica, it doesn't automatically add the u of t. So this is just getting the inverse Laplace transform of this. This is what it looks like. And if I plot it in our simulation, let me do the root locus again. We looked at the root locus and we said we wanted to go all the way to a gain of 1960. So this is where we should be. If I don't put any gain, I'd be here. I'd be something like this, like close to this place. So here I have to make the gain 1960. So it's not just 2 zeros, also the gain is 1960. Right? So now I'm going to get something that's closer to my simulation, hopefully. And yeah, so I get something that is pretty almost identical. Well, it is, I mean, we're not plotting it on top of each other, but it looks identical to the simulation. almost identical, and this should be the correct response, right? This is this is not going to be exactly identical because I haven't included the pole at minus 100 actually. So coming back, this looks close to my response. The only reason there's a slight difference is that in my simulation, so that I can get I can mitigate the effects of the differentiator in the simulation. I added the pole at minus 100. What happens if I go back to my simulation and put, for example, 1000 here, put the pole at 1000? What will I get? Let's see. Yeah, I get something even closer to my theoretical curve. So you notice the curve here doesn't hit 2. Here it also doesn't hit 2, and it settles around the same place. Settles around the same place. So it looks pretty much identical. Let me go back to 100. And now let me add now the other controller. The other controller is the PD block that MATLAB has. And this is essentially the same thing, only it's integrated within MATLAB, and it's just the same thing that we did in the first situation, right? So filter coefficient is 100. The pole is essentially the pole at minus 100. Pole at minus 100. So if I add that in and run this, the two curves match each other. The yellow and the blue exactly match each other. So this is good. However, if I go and apply it differently, if I now use the delta U by delta T block and put the pole at minus 100 after the delta U by delta T block, delta U by delta T block is also differentiation. It's the same thing. I mean, it should be the same thing. However, when I do it this way, so I didn't do anything drastically different here. I just have the differentiator with the pole at minus 100 after it. Right, this is the normalized pole. So this is at s equals 0, the gain is 1 for this block. Right, differentiator pole. This should be the same thing, you would think, but when I run this, I have to connect it. When I run this, I get a drastically different response. This is absolutely incorrect. And the reason this is incorrect is this block. You should never use this approximation for differentiation, this delta U by delta T. This numerical approximation for differentiation should never be used in a negative feedback model, simulated model in a simulation. We can use it when we do analysis, so it's fine using the 1 plus s over 3 when I'm trying to do exact analysis and I solve everything symbolically as like Mathematica allows me to do. So it's absolutely fine to do it analytically and it gives you the right result. However, whenever you try to do this in simulation, this is going to capture any step function, any place where the input or the signal changes instantly. This is going to capture that instantaneous change, and it's going to cause a huge numerical error. Clearly, it's going to cause a huge numerical error because step is going to propagate, right? Because the step is going to the output of this step for this differentiator is going to be like an impulse. And this impulse doesn't show up when we do the exact analysis because, we are doing exact analysis. Everything is taken into account all at once. However, when we do a simulation, everything is calculated step by step. So because nothing is solved all at once, like an analysis, in the initial steps, some impulse is going to show up that shouldn't show up, right? So you're going to get an erroneous, an incorrect response. The point is that whenever you're doing negative feedback simulation, avoid using this block, this derivative approximation like the plague. It will absolutely give you an absolutely incorrect result. This is absolutely incorrect. No way around it. while those two give us the right result. So this thing and the blue and the yellow curve, right? This matches our analytic, and we know that this is the right result because we compared it to the analysis, to the exact analytical solution that I've found using Mathematica. I want to experiment with something. Let me see if I move the blocks like that. Would that matter? It shouldn't matter because those, well, you think it shouldn't matter. See, that's the thing. Analytically, theoretically, it doesn't matter if I do this swap because this is linear, this is linear, right? This is linear, this is linear. Doesn't matter if you do the swap. Analytically, it all should be the same. However, numerically, because the numerical simulation is going step by step, the signal is propagating. So I want to test if the signal propagates through the filter first, will that affect the result? Right? This, if it does affect the result, that would only have happened due to numerical nonlinearities. What do you know? Yeah, this is bonkers, actually. This analytically, theoretically, this doesn't make any sense. And the reason this doesn't make any sense is because it doesn't matter whether we swap those two or not, right? Because blocks are commutative. This is a linear system. Everything is commutative. It doesn't matter if you differentiate and then filter or filter and then differentiate. However, because this is an approximate simulation and the differentiator captures impulses, because this is, let me phrase it this way, because this is a numerical simulation that instead of solving everything analytically all at once, like we do when we do analysis, it is going step by step and signals are propagating, right? And in analysis, the whole feedback loop is solved all at once. You find the analytical solution all at once. In a simulation, signals propagate through the loop, and it does matter. It is, this is a sign of nonlinearity, by the way. It does matter only for the simulation where the signals propagate first. Okay, so in this case, we avoided this error due to the integrator, so due to the differentiator, by having now the filter come before the approximate differentiator. Okay, so this is bonkers. This is analytically shouldn't matter, but because this is a approximate simulation, that it does matter. And because this guy is bad, this guy is not good to use. It's not good to use this guy delta u by delta t in a simulation, in a numerical simulation, right? This filtering just mitigates the issue, right? So it seems if you want to use this, that's the trick. Put the filter the signal before it reaches this. So this prevents any sharp edge from feeding into this approximation of the differentiator of delta u by delta t, or S. However, I mean, the best thing to do is don't use this at all, right? This is my advice. Don't use this at all, right? So this solved our issue, but don't use it at all. If you want to use a differentiator, use something like this, where you add a pole already, and then you write the differentiator this way, or use one of those blocks if you want. I typically don't like to use those blocks, especially when I am learning or you are learning, because those blocks kind of like hide stuff from you, right? And it makes it harder to learn, right? You can use those blocks only after you are, well established in using this tool. All right, so there you have it. Hope this clarifies a bit of the simulation issues that we went through. And again, simulation is always an iterative process, right? And this also demonstrates the importance of trying to kind of do tests like that, like doing you don't always, you cannot always do like an analytical comparison, because not all systems you will be able to do like a analytical solution. But in situations where you can do that. Or if you could sometimes do is you could test a simplified system that you can solve analytically, and then compare with the analytical solution, just so that you can make sure that whatever you're doing in the simulation makes sense, right? So you would kind of, if you have a complicated system, you could start simulating a simplified system, and then just to make sure that your simulation makes sense. You know, it doesn't give you something that's problematic. All right, so with that, we'll continue next time. I just wanted to kind of, I wanted to clarify this outside of lecture time, so that we don't waste lecture time, because I want to go through the motor control project next time. Semi-project. I mean, it's going to be a short project that we do in class. All right, thank you, and I'm gonna upload this, and hope you can look at it before next class. Thanks. Bye.